Bismillahirrahmanirrahim. If you recall, last time we talked about transformations, and we said there were four types of transformations: translations, reflections, rotations, and dilation. Last time we talked about reflection and how we reflect objects in a Cartesian plane. Today, inshallah, we shall talk about translations, and these are also known as slides or glides. So translations are a type of transformations, and they have some synonyms. They're also known as slide or glide, or sliding an object or gliding an object. So it goes by several names. So our objective today is to appreciate translations. Appreciate, that is, a little bit more. So here I have a triangle, and I'm going to translate it. That is, I'm going to slide it like thus. There it is. So I've taken the triangle and I've moved it in this particular direction, and that's called a translation, or a slide, or a glide. So taking an object and moving it in any specific direction is called a translation. Now, if you appreciate, if we could label the vertices here of the triangle like this, let's say triangle ABC, that's going to be the pre-image, and triangle A prime, B prime, C prime, that's going to be the image. So I've taken triangle ABC and I have translated it, and the new image is the triangle A prime, B prime, and C prime. Now, what's happening here is every point that's on the triangle is getting moved to in the same distance, in the same direction. That is, I'm taking point A and moving it to point A prime, and point B to B prime, and point C to C prime. Correct? So when I'm moving this triangle, I just have to move the vertices, so to speak, and then connect the dots. And I'm moving every single point that's on the triangle in the same direction and the same distance. So this segment here, this particular arrow, is of equal length, and it's in the same direction. And that's what a vector is. So a vector is, at least in my mind, a segment that has a specified length and very importantly, and a certain direction. For example, if somebody comes in and you're standing, on the street, and somebody says, "How do I get to the library?" And then you say, "Okay, you walk 2 miles." I mean, 2 miles in what direction, right? So, or somebody says, "Okay, I want to go to the ice cream store," and you say, "Just go east." I mean, like, okay, east, fine, but east in direction, but in what length? How far do I go east? Do I go like 50 yards? Do I go like 10 miles, right? So in defining direction of movement, you have to define both the length, how far an object is moved, and in which direction an object is moved. And vectors in this regard are very, very useful. Vectors are segments that have specified length and a specified direction. So you say you go due north, 3 miles. You go due northwest, 3.5 miles, etc. So vectors are segments that have specific length, and also they have a direction. And in this case, the same vector is used to move every single point. So it guaranteeing that the whole object gets moved in the same length, and the whole object gets moved in the same direction, so the object's shape and size does not change. Right? If I moved A in a certain amount of direction, but I moved B a little farther, a little closer, the triangle is not going to look the same. So vectors are very useful in translation because they allow you to move a certain object in the same direction, in the same length, without changing the shape of the object. Now, so the vectors like this are given names. You can give this name, like you can write them like segments do, like A, B. So if you were to write this as a segment, right, you would say this is segment A prime, correct? So that's segment A and A prime. So, but a vector, you can write it like this. Ta-da! So this symbol here is a symbol for vector. All right, so you can use endpoints to name vectors. Okay, so in this case, the endpoints being a and a prime, or you can give it lowercase letters. Let's call this vector w. So this is a lowercase w, and you put a little vector symbol on the top to suggest that that's the name of the vector. So vectors are named in two different ways. So you can name them using the endpoints, or you can give them lowercase letters like this and put the little vector symbol, which is, I think, pretty cool symbol, right? So I just want to bring to your attention the symbol for vector is this, and if you were to go like this, that's not a symbol for vector. This is, of course, an array, and this is a symbol for a vector. Okay, so this is vector w. So you move point A in the direction of this vector w, and you move point B in the same direction as in the direction of the vector w, and you move point C in the same direction as vector w in the same length, and you move the whole triangle in this way. So you can see how beautifully and important and easy vectors make moving objects in a certain direction. So again, vectors are segments that have a specified length and a specified direction. Now, we can use the vectors in the Cartesian plane, and because most of the geometry that we're going to do over here, moving objects in a Cartesian plane, it helps considerably, because then you can define exactly how far in which direction you're going to move. So this particular example I gave you for here, we said this, we could call this vector w. So here's vector w that we use to translate this particular triangle in this particular direction for that distance. So if I were to draw out this particular vector, in this Cartesian plane that I have over here, I could say approximately it looks, I'm guessing, this is like vector w. Okay, so now here's a vector that I've drawn over here, and I'm going to call this is my vector w. Now notice this does not represent a ray over here in this particular case. In the Cartesian plane, the vectors are drawn like this. That is, you're moving this particular point in this particular distance. So don't confuse the end arrow over here as representing a ray. So this does not represent a ray. This, in fact, is a vector that has the two endpoints from here and over here. In fact, if you were to give this particular vector a name, let's say this is A and this is A prime. This, sorry, I meant to say A and A prime. Okay, as I said, you can also use the endpoints to name the vector. So you can call this vector A prime, or simply vector w. Okay, now a couple of things about vectors. Okay, now this vector is the same as, now I can move this vector. The beauty of vectors is that you can use them to move things, right? So if I move this vector anywhere along in the Cartesian plane, so I'm trying to make this vector the same length as this one. So if I just move this whole vector over here like this would still be vector w. In other words, vectors are free of movement. So these are not two separate vectors. These are going to be the same vectors, assuming that I've drawn them accurately and that they're the same length and in the same direction. So here's again vector w, which is the same vector but moved away slightly different in a different area of the Cartesian plane. But as soon as I change the direction or the length of the vector, it no longer is the same vector. In other words, I have vector w here, and if I were to draw the same length vector, but let's say in this direction, that's no longer vector w. That's a different vector, because two vectors are going to be the same vector if they have the same length and if they have the same direction. So two vectors are the same if they have the same length and the same direction. Two vectors are not the same if they have the same length but the different direction. And two vectors are not the same if they have the same direction but not the same length. So for two vectors to be the same, they have to be congruent, let's say, they have to have the same length and the same direction. So this green vector here, you have to use a different name for it. Let's say vector v. All right, so vectors can come in different sizes too. Okay, here's a tiny vector over here. Oh, that's not the best vector I've ever drawn. So here's a tiny vector over here. Okay, we can call this vector P. Ta-da! Right? So they can come in different shapes and different sizes, and here's another vector. Okay, we can call this vector K. All right, so now, a vector is the same as long as it is in the same direction and in the same length. Now, so I've drawn over here a vector V. Now, this vector has these two endpoints here, C and D. So I can also name this vector using the two endpoints. I can call this vector CD like this. Now, notice over here, I moved the vector D over here, vector V, in quadrant number 2. Now, it's the same vector because it's the same length and the same direction. So vector, in other words, they have the freedom to move in the Cartesian plane, and they will be the same vector as long as their length and the direction is the same. Now, but in talking about vectors, therefore, they're free floating, right? If you want to talk about the particular vector, it's useful to put one of the endpoints over here, the beginning of the vector, the starting point, and the ending point. The beginning of the vector here, the origin, and because if you kind of station the vector at the origin, if you pin the vector, so to speak, to the origin, you can define which direction it's going, right? So if you want to talk about a vector in a more scientific way, you pin it to the origin. I mean, you bring it to the origin, you glue it to the origin, and then you can determine the direction of the vector. So in defining vectors, you put the vectors in the origin and say, okay, this vector is CD over here, it's going in this direction. And then you find the endpoint over here, and the endpoint is, let's say, it's going to be 3, 2. It's the ordered pair 3, 2. So point D is 3, 2. And we use the endpoint, right? We use the endpoint to define vectors. In other words, you can write this vector symbolically as V with a little vector sign, or using the two endpoints, CD, capital C, capital D, with the little vector point, and you can define the vector precisely, that is, its direction and its length, using what's called the vector's form. That is the vector form. That is, you can write this vector and you can define this vector and say, okay, well, this begins, if you put it at the origin, is 0, 0, this vector can be defined as, or written as 3, 2. Now, this is called the component form. This is called the component, component. That's the component form of writing a vector. That is, it gives you the x component of the movement, right? And it gives you the y component of the movement, and it defines the vector for you. In other words, in the x direction it goes 3 units, and in the y direction it goes 2 units. And that's how you can write different vectors. So this form is called the component form. So we've learned 3 ways of writing vectors. This is 1, this is 2, and you can precisely define a vector as 3, 2. So you read this as vector 3, 2. Now, if I have another vector, let's call this vector T over here, and I'll give you the component form of the vector like this. Okay, component form of the vector is 1, 4. Okay, now this is not an ordered pair. As you can see, it's not the parentheses like this. It has this like this vector symbols over here. So this is not a less than equal sign. This is not a greater than equal sign. It's like parentheses with sharp parentheses, if you like. So this is the component form of the vector. So if I were to draw out this vector, I simply find the endpoint of the vector 1, and this is 4 for me. This is going to be 2, and this is going to be 4. So that's that. And I can draw the vector out simply like this. Okay, so this is vector T. Now I can move vector T anywhere in the Cartesian plane, and this would also be vector T right here. I'm sorry, I kind of messed it up. So I moved it here, see? So as long as I do not change the direction of the vector or the length of the vector, it can move the vector along. in the Cartesian plane like that. All right, so this is called the component form of the vector, defining the vector using its tail and the tip. So this end of the vector is called the tail of the vector, and this end is of course called the tip of the vector. So in the component form, you can find the tip of the vector by going to the origin and going to the ordered pair represented by the tip over there. So that's how you write vectors in a Cartesian plane. Now let's see how useful this is in translating figures in the Cartesian plane. Okay, so here's the question. The question states, translate the figure JKLM using vector 1, 4. Now vector 1, 4, if you were to draw it out, is 1, 4 like this. Okay, so this would be the vector we're going to use to translate this. In other words, move this whole entire figure in that direction, that distance. So let's give this vector a name. Let's call this vector, I don't know, I like to use V. Let's call this vector V. So we're going to translate this whole quadrilateral in that direction, kind of like north, east, mit, and in that distance. To do that, basically, we have to move every single point on the quadrilateral in that direction for that distance. Now, we don't have to move every single point. We just have to move the vertices, and once we've done that, we have basically moved the whole figure. So first of all, let's label the vertices. So this looks like this is -2, -2, and this looks like 0 and -3. And this looks like 2, -2, and M looks like 1, -1. So what I do is I can, in order to not make a silly math mistake, you can just write J, you can write all the ordered pairs. J is -2, -2, because I'm just telling you it's easy to make silly math mistakes in this KX 0 and -3, especially when you're talking and writing at the same time. So 2, -2, and M is 1, -1. So we're going to move each endpoint using the vector V. So here, if you take this point and then like this, so to speak, and then we use vector V over here. If you apply vector V, let's call this vector V, and we're gonna do the same thing over here for each one of them. So this arrow here does not represent the vector. This just represents where it's going to go here. Okay, so so I'm putting double arrow just to make sure we're not confused with that. Okay, so in other words, if you translate J using this vector, well, all you have to do is you have to add 1 to this and to the x value, and add 4 to the y value. For example, if I take this and use the vector V, so I add 1 to here and 4 to here. So let me see, let's go up to, okay, here we go. So J will be moved in this direction right here. See, that's the vector V. So if we apply vector V to J, J will become J prime and end up over there, right? So in order to do that, you simply you add each component of the vector to the ordered pair. So when you do that, if you add 1 to -2, that will become -1. And if you add 4 to -2, that will become 2. And that's kind of what I have here, don't I? I have -1. Let me write that ordered pair over here. So this is -1 and 2, right? So now notice, this is the vector. Notice how I wrote that with the pointy brackets, and this is the end point. Okay, so J will become J prime, and that would be the endpoint. So, and then if I apply the same vector to each one of these endpoints, I got 1, 4 over here. Let me just write those down. Okay, 1, 4 over here. I'm going to apply the same vector in its component form to each one of the endpoints. So K will become K prime. So if I add 1 to 0, I get 1. And I add 4 to -3, I'll get 1. And here I'll get L prime, and if I add 1 to 2, that will become 3, If I add 4 to negative 2, that will become 2. That's the ordered pair. And m prime is going to be, that's 2, and add 4 to negative 1, that becomes 3. See? So you can see it becomes, it could be easy if you were not organized like this. So I really encourage you when you're moving like complex, like figures like this, to write each individual endpoint down and what it translates to. So J will translate to J prime, K will translate to K prime, and L to L prime, and M to M prime. And it's important to keep yourself organized in this way. And after you've done that, you can simply draw this out. And let's use purposes here. So J prime is going to be here. So that's my J prime. Negative 1, 2. And K prime is 1, 1. So K prime is like over here, 1, 1. That's K prime. And L prime is 3, 2. That's 3, and that's 2. And M prime is 2 and 3, assuming I did everything correctly. I'm pretty good. So, and then I just connect the dots, right? So here it is. Ta-da! So that's L prime, and that's M prime. So I have moved the entire figure in this particular, using this particular vector like this. See? There you have it. Okay, so that's how you use vectors to translate figures in the Cartesian plane. So as a review, vectors are very useful. Vectors are segments that have a particular length and a particular direction. Okay, direction. Okay, so that's very important, and they can be written using lowercase letters, or they can be written using their endpoints, the tail and the tip. So they have a tail and a tip. You can use the endpoints of the tail and the tip to represent, or you can use the component form of the vector. The component form basically gives you the change that occurs in the x direction and the change that occurs in the y direction. The component form here is not an ordered. It's not an ordered pair per se. It tells you where the tip of the vector ends. So it's a representation of the vector if you were to pin the vector in the Cartesian plane. And you can to use vectors to translate figures. You simply take the endpoint of the figures and apply the vector to each. That is, you add the x component to the x value, and you add the y component to the y value to get the image from the pre-image. You can use vectors to translate triangles, quadrilaterals, or whatever you want, or you can use even vectors to translate single points, such as it can be translated to A prime using this particular vector. You can call this vector K, for example. So you can translate points, you can translate segments, you can translate triangles, you can translate quadrilateral, pentagon, whatever you want using vectors. You can see how beautiful, how important, and how elegant and useful the vectors are. Inshallah, until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.